Good morning, everyone. All right. Hope everyone had a good weekend. So today's going to be totally review. And this usually works a little better on a giant chalkboard, but we'll make the best of it here. Everyone can hear me okay? Yeah, okay. All right, so yeah, I'll just spend today's lecture reviewing SN2, E2, and nucleophiles leaving groups, substrate effects. And, I was thinking about this over the weekend. I think the take-home message of this chapter, okay, as I've said before, but I think of a better way to say it now. I think the take-home message is it's going to be very hard, to draw hard and fast lines in the sand as to how, reactions are going to proceed. You have to, as I've said, you have to consider everything. That being said, we're not going to present to you, and in practice as well in the lab, you're often not presented with situations that can't be engineered to go one way or the other, to go SN2 or E2. And so as that is the case in lab, that will be the case on the exam and problem sets and, probably the MCATs and everything. There will be specific conditions, indicators, reagents, substrate structures, that when you have one or two of these, you're going to see that it's going to have to go, say E2 versus at the expense of SN2 or something like that. So don't worry about, trying to generate some matrix of all possible conditions and then, determining, which way each of those conditions is going to go. You're going to be presented, with things that are hopefully not ambiguous. Okay, I don't know if that helps to clarify it all or not, but anyway, hopefully we can make this clear here. So SN2, E2 review. Oh, the other thing I wanted to say was that so the exam Friday, same format, take home 12 hours. Trying to streamline the scheduling a little bit. So I made an ungraded quiz that went out this morning. It's due Wednesday at midnight. Let us know 9 to 9 Friday, 9 to 9 Saturday, or if you've got commitments that don't allow you to, get sort of the full 12 or nearly the full 12 hours, you can specify, you can propose another time or day. We'll most likely approve it, obviously, but, pending approval, and then we'll get the exams scheduled. So you don't need to email me directly this time. Please just complete that survey. Should make it a little more efficient. All right. So we're going to talk about SN2 and E2 together, okay? And we'll start with our friend, the SN2 reaction. And maybe I'll try and see if I can fit them both on the same whiteboard here. This may get a little crowded, but might be better. All right, so for both of these transformations, you have a reaction. Both proceed in a single step, okay, through a single transition state. There are no discrete intermediates along either reaction coordinate. So Okay. And then both of these reactions had a distinct stereoelectronic requirement, right? Does anyone want to fill in the blank here for SN2?
SN2 is going to be inversion of stereocenters?
Yeah.
Is that what you're looking for? Okay.
Yeah. Right. So SN2, inversion of stereochemistry, right? And we said backside attack. That's how you get the inversion, right? So I'll write that here, backside attack, inversion of stereochemistry. Right? And remember, when this is, when we say inversion in this context, we're talking about physical inversion. You're physically inverting the stereochemistry at the carbon. That will often lead to R going to S. But keep in mind that the RS nomenclature has no bearing on physical orientation. So, if the substituents in the leaving group are sort of correctly arranged, you can have R go to R and still have inversion. It just depends on the priorities of what's incoming and leaving. But in this case, the inversion means physical inversion at carbon. So let me. Okay. And then how about the E2 elimination? What's the stereochemical requirement for that? Yeah, Caroline.
Would it be the alkenization of the molecule along an alpha beta bond?
Yeah.
And elimination of a beta hydrogen?
Yeah. So you eliminate a beta hydrogen. The CC bond becomes a double bond. But what about the orientation of the hydrogen you're eliminating and the leaving group?
They're anti?
Yeah, anti-periplanar, right? So we say that anti-periplanar arrangement of CH to be eliminated, CX, I'll say is optimal, because the other option is a syn-periplanar arrangement. So let me just come to that in a second. So in other words, okay, the dihedral angle, another way to say anti-periplanar is to say that the dihedral angle between the carbon-hydrogen bond and the CX bond is 180 degrees, okay? And so we'll talk about that in orbital terms in a second. But then the other option, which is not as good, okay, higher transition state, but still possible, is syn-periplanar. And I'll say syn-periplanar is second best. And you'll know that that means that if the substrate can't do an anti-periplanar reaction, you're going to look for the syn periplanar elimination. And in that syn periplanar arrangement, I've got the CX bond coplanar with the CH bond that I'm pulling off, syn coplanar, and so the dihedral there is 0. Okay. And what is not tolerated, what we can't do is, and there's no real term, well, there's a term. We can't do an elimination where the CH bond and the CX bond are orthogonal, where that dihedral is 90 degrees. Those eliminations do not proceed. So okay. And so, so we'll talk about the orbital interactions in a second, but I just wanted to say, you know, there's a steric basis. There's both an orbital and a steric basis for favoring the anti-periplanar over the syn periplanar. And should the text in red say, oops, sorry, thank you. Yes. 90 degrees orthogonal does not proceed. The anti-periplanar elimination for steric reasons is better than a syn periplanar, because if you look at the syn periplanar conformation here, this is all eclipsed, right? And so we know that that's generally not a favorable situation. In the anti-periplanar, you're staggered. Okay, and so if we just, you know, forget about the elimination pathway for a second and reflect on the favored conformation of the molecule, we know that staggered is always better than eclipsed. And so to get to the syn periplanar arrangement, you have to access a higher energy conformer. Not impossible, but it comes with a penalty associated with it. And in fact, you know, most of the syn eliminations that we see come from a situation where the substrate is locked in like an eclipsed conformation, like a, you know, a fused bicyclic system or something. So, all right, so the next slide we'll talk about the orbital interactions, and that'll give us also an explanation for these stereochemical requirements. So let me proceed. Okay, so what is the orbital on the substrate that I'm thinking about when I do an SN2 inversion? What do we say that the nucleophile attacks? Yeah, Ghana?
The sp3 orbital of the carbon.
Can you be a little more specific? So what bonding or anti-bonding orbital is it attacking?
Is it the bonding orbital between the carbon and the leaving group?
Close. It's the carbon leaving group anti-bonding orbital.
Oh, for SN2 as well? Okay.
Yeah, for SN2. Yeah. So let me draw that out. So so orbital interactions, here's the substrate. Here's our carbon. And let's just use, excuse me, we'll use a real substrate. We'll put a chlorine on there. Okay. So methyl chloride. And so remember that going back to the beginning of class, when you have a heteroatomic bond, so the atoms are not equal, the bonding orbital is polarized towards the more electronegative atom. And there's this theorem of quantum mechanics that says the sum of the square of the coefficients of the molecular orbitals on each atom must equal 1. And so the molecular orbitals of interest are the bonding orbital and the anti-bonding orbital for the carbon leaving group bond. And if I'm tilting the bonding orbital towards the leaving group, I have to tilt the anti-bonding orbital towards carbon, okay, to satisfy that requirement. And so the anti-bonding orbital looks something like this. Okay. So this is sigma star CCl, okay? And that is polarized towards carbon. And speaking very colloquially here, most of it is behind carbon. So large lobe behind carbon, okay? And this is a little bit more than you need to know, but just to kind of, for those of you that are interested, you know, why don't we attack the CH bond, right? If we're just thinking about bonding orbitals and anti-bonding orbitals and not thinking about leaving group ability for a second, why not just have the nucleophile interact with the CH bond? And the reason is the sigma star is what we call the lowest unoccupied molecular orbital. So if I were to insert a little reaction energy diagram, we would have sigma star CH, sigma star CL, sigma CL, and then sigma CH, okay? Again, you don't need to worry about all this too much, but just to show you where this argument comes from, the CH bonds are very strong, right? They're much stronger than a carbon chlorine bond. You know, you're talking 90, 95, 100 kcals per mole versus I think about 80 for a carbon or 70-ish for a carbon chlorine bond. Okay, so what does that mean in reality? That means that bonding orbital is very low in energy. Okay, and so when I have a very low energy bonding orbital, I generate a very high energy anti-bonding orbital. And so the CH bond, the sigma stars, are all the way up at the top of this little chart. Okay, because the carbon chlorine bond itself is weaker, the anti-bonding orbital is also lower in energy. It's putting electrons in there is less destabilizing, and so it is lower in energy than sigma star CH. And so when nature, when I'm a nucleophile and I'm kind of hunting around for an orbital to interact with, I don't want to go for a high energy orbital. I want to find one that's close to me. And the carbon chlorine bond is the one that's closest. And so we refer to this as the lowest unoccupied molecular orbital, or the LUMO. Okay. But again, this is not something that you need to be able to recapitulate, but just to give you an understanding of where these statements come from. Okay. And so sigma star CCl is polarized towards carbon, and most of it is localized behind the carbon. And so as my nucleophiles coming in, I get maximum orbital overlap if I attack from the backside. So Okay. And so my nucleophile, let's say I'm going to bring in I minus. That's going to come in with its own orbital. Let's find a new color here. Okay, and that will come in from the back side. If you come in from the front, say I were to attack here, okay, you would get both constructive and destructive orbital interactions because of the change in sign in sigma star. So that does, the net effect is no bonding interaction. And then, you could say, well, something crazy, why not attack there? And the answer is, both carbon is a terrible leaving group. And then also there is very little of that sigma star. So even if the carbon were somehow activated to be a great leaving group, there's not a lot of orbital interaction to stabilize the transition state. I don't know, did I show you guys the Klopman-Salem equation way back at the beginning of class? No? Okay. Well, anyway, there's a useful equation that comes out of quantum, which can actually be simplified to the point that I should have given. I mean, I'll give it to you on Wednesday just for fun. Anyway, the Klopman-Salem equation basically tells us that the strength of a bonding interaction depends on two things. One is the extent of orbital overlap, how big the lobes are and how much they sort of overlap. And then the second is an electrostatic interaction. I'll pull that out and give it to you because it's just a cool thing to talk about. But anyway, the more sort of lobe, the bigger my lobe, the more my lobe can overlap with another lobe, the better that is. Okay, just think about it like that. All right, so let's do E2 elimination. Okay, and we'll just focus on the anti. So let me generate a substrate. So we'll say again, let's do Cl. Okay, so this one's a little more complicated because I've got a little bit more to think about. So I need to think about sigma star of the carbon-chlorine bond, okay? And so forget that we're doing an E2 elimination. We already constructed the sigma star. It's on the left of the slide, right? And so that's going to be identical. So we know that it's got a big coefficient behind carbon. We know that there's an anti-bonding interaction between carbon and the chlorine. And we know that the chlorine doesn't have a whole lot of it behind it. And so this is sigma star. So exactly the same as what we have on the left, as you'd expect. What's interacting with that is the adjacent beta CH bond. So alpha, beta, okay? And when I say, when I say the CH bond is interacting, what I actually am saying is that it's the sigma bonding orbital, which has its 2 electrons, that is interacting. So sigma, okay, like that, all right? And so this is what we call the stereoelectronic. So the sort of the electronic interaction that requires a particular spatial array or spatial orientation of your groups. It's the stereoelectronic basis for the anti-preference in the elimination. So that CH bond is going to be dumping electrons into sigma star in the transition state. So Okay. And, you know, I always try to tell you guys, think by analogy, right? So this orbital interaction is strictly analogous to hyperconjugation, right, in a carbocation. So if I drew a carbocation, why am I? So if I drew a carbocation, let's just get rid of maybe the chlorine, have the exact same substrate, right? Now, if this is positive, this orbital on carbon is no longer an antibonding orbital, it's just an empty orbital. Right? And we said that, you know, more substituted carbocations are more stable because you get an overlap of the adjacent CH sigma bond. So okay. So does everyone see the homology between those two systems? You know, filled, overlapping with empty. You know, the only difference is that I've changed one of the orbitals. So I've changed it from an empty 2p orbital to a sigma star in the elimination. But you can construct the same, we did the orbital diagrams for hyperconjugation. You can do the same thing here, okay? And obviously the placement of the AOs and the energies of the resulting MOs are a little bit different, but qualitatively the trends are exactly the same, okay? And so it's that donation that is important in the transition state. And I want to, let me just, I'm going to continue this on the next slide because we need to talk about what's happening between the base and the CH bond. So let's see here. Okay, and so we drew the sigma star and the CH. Let me just draw out what's happening. Oops, that's chlorine. Between the base and the hydrogen that's being eliminated. So the base is going to come in and attack the CH bond, remove a proton, okay? The MO description of that is that the base comes in and attacks sigma star of the carbon hydrogen bond. So draw that here. So lone pair on base attacks sigma star CH, okay? So there's kind of two things that are going on with the E2, and it's a little, you know, tricky to draw it all, to draw the orbitals in one diagram. So this diagram is overlaid with what we drew on the last slide, okay? It's all happening at once, okay? So the base is attacking sigma star of the CH bond at the beta position, okay? At the same time, the sigma CH bond is starting to donate into sigma star CCl, okay? And again, think about this, think about it from the standpoint of, sort of what's happening with the orbitals. So if my CH bonding orbital is down here and sigma star is up here, right? That's like a nice, just normal bond. As I start to populate sigma star CH with the base, what am I actually doing in practice? I'm weakening the bond. And so I'm pushing the energy of that, the electrons in the CH sigma bond up, right? And we know that the carbon chlorine sigma star is somewhere over here. And so as I elevate those electrons in the bonding orbital and energy, they're getting closer to sigma star. And so you're getting a stronger interaction. And so that's why it all kind of has to happen at the same time. All right. All right. And so what do we say that the transition state looks like? Let me just maybe stick with E2 since we're on that topic. So so for E2, the carbon is starting to planarize in the transition state. So remember, this is going to become an alkene. So it's going to be somewhere between tetrahedral and planar, okay? And your orbitals on carbon are starting to look more like normal 2p orbitals that we see in in a double bond. So I've got something like that. My chlorine is now taking electrons. Sorry, that's cut off, but you get the idea. It's starting to accumulate negative charge in the transition state. And the base is picking up that hydrogen. Okay, and it's starting to accumulate, if we start with a negatively charged base, we're starting to accumulate positive charge in the transition state. Okay, so carbon, I'll write it over here. Carbon starting to planarize. C orbitals look sp2 like, or sorry, 2p. And then delta minus on leaving group, delta plus on base. Okay. What do I mean? Let me see here. What do I mean by carbon starting to planarize? Yeah. So what I mean is that in the starting material, the bond angles here are about 109, right? And when this thing gets to be fully converted to product, we know that we're going to have a double bond. And so the carbon will be planar. The bond angles will be 120 degrees. And so by starting to planarize, what I mean is in the transition state, you're somewhere between tetrahedral and fully planar. Okay. And so, these hydrogens on the side here, I've intentionally sort of pushed them down a little bit. And these guys are starting to come up relative to the starting material. Okay. So the geometry is kind of, between the product, which is fully planar, and the starting material, which is fully tetrahedral. The transition state is somewhere in between. Okay. And where exactly it is in between, depends on the reaction conditions, but the important point is to know that it's somewhere in between, okay? All right, so let's do the same thing for the SN2. So we drew the orbitals for the starting material, so we can just kind of move that down there. And then in the transition state also is quite interesting. So in the transition state, the carbon has what geometry? Does someone want to help me out?
It's like trigonal bipyramidal.
Yep, exactly. Trigonal bipyramidal. It's frankly my favorite of all the geometries. It is sp2 hybridized. So the trigonal bipyramidal, remember, that refers to the whole ligand sphere, right? It's like how many things are around carbon, where are they pointing? Same thing as when I say like tetrahedral, right? Those terms, 90% of the time correlate with the hybridization. So the trigonal bipyramidal carbon is going to be sp2 hybridized. And the key orbital that we need to think about is the one that I've drawn. That is a 2p orbital on carbon, okay? And that 2p orbital is interacting with the orbital from my nucleophile. And also interacting with the orbital on the leaving group. Okay. And so carbon is sp2 hybridized. The bond angle between the nucleophile and the leaving group is 180 degrees. So oops. 180, 180 degrees. And then the bond angle between the substituents on carbon is 120. I'll just say the H is 120. So whatever's attached to carbon but not participating, that angle is 120, this angle here. Okay. So, okay, so those are the two transition states. And now we'll get into substrate, leaving group, nucleophile. Any questions on what we've done thus far? Yeah, Ghana.
Can you go over how the S2p or sorry, the C2p orbital is derived? Like, I know that comes from the bond between the carbon and the leaving group, but how does that transformation occur?
Yeah. So so the way to think about it is the following. Okay. At any given instant, as the reaction is proceeding, the carbon's going to have the hybridization that maximizes the bonding interaction. Okay. And so it is, from a quantum mechanical standpoint, it is 100% legal to say I've got carbon as sort of sp3 like one instance, and then say, as I go sort of incrementally just a little bit more along the pathway, all of a sudden it starts to look more sp2 like. Okay. And so starting material is sp3, the transition state is sp2. Every little point along that curve is somewhere in between. And it's kind of a continuous, sort of transition. So how does it get there? It kind of gets there, in little sort of increments as you start to change the geometry. So if you were to think about it from like, if you were calculating it, trying to quantitate it, at various points along the pathway, all of these in the middle would wind up being in between, but they would start to look, a little bit more like SB2 as you got closer to the transition state. So it's a slow, gradual change. Nature doesn't know that it's planar. Those are just terms that we use, but it's happening sort of in between. Hopefully that clarifies it a little bit. Yeah. Nature can always do whatever it wants to get the most bonding interaction, to get the most low energy. It can just flip around and do whatever it wants. So, okay. Any other questions? Wendy.
Is there a particular reason that you're calling in one case the base and the other case the nucleophile?
Yeah, for sure. Good point. So yeah, anytime I'm attacking a hydrogen, we call it a base, right? Anytime I'm attacking at carbon, it's a nucleophile, okay? And, those two together are what we want to sort of carefully call the reagent, okay? And so you have your reagent that's interacting with the carbon, depending upon where it decides to go to carbon, or interacting with the substrate, depending upon where it wants to go, carbon or hydrogen, it's a nucleophile or base, okay? Yeah.
Thank you.
Anyone else? Maybe just speak up, because I can't, if you have a question, because I can't see everyone with the screen up here. But okay, I'll keep going then. Okay, so talk about the stereochemical outcome. SN2 is easy. We already said this. This is inversion. Not going to say too much more about that. E2, there's an important point here, okay? Which is that, rarely are we going to do an elimination to make ethylene, right? An unsubstituted olefin. Usually, you're going to have substituents on carbon. And the question is, if I have substituents, we know that cis-2-butene is different than trans-2-butene, right? They don't interconvert, right? And so we want to be able to think about how will the substituents orient themselves in the transition, in the product for the E2, right? And the way they do that is a consequence. Where they end up is a consequence of the geometry of the starting material. And so what we'll do is we'll put all of these as just R1, R2, R3, R4. So these can be anything you want, hydrogen, whatever, carbon, oxygen, whatever you want. Because I have to have this anti-periplanar orientation of the CH bond and the CCl bond, okay? R2 and R3 will always end up on the same side, and R1 and R4 will always end up on the same side, okay? So if you consider, this was probably actually a good time for a Newman projection. If we do a Newman projection and we look down that bond, so I've got R4 over here, or R3 over here, R4 over here, chlorine going down, and then the carbon in the back, I got my H atom of interest going up, R2 on the left, and R1 on the right. Hopefully this helps, right? So that's the Newman projection of the conformation for the elimination, okay? And we said that E2 goes through a single transition state, there are no intermediates. So what does that mean? It means you don't have time for bond rotations, okay? You don't have time to do anything to the molecule. And so sort of the conformation that it's in as it enters is the conformation that it will come out in, okay? And so if we process these through an elimination, okay, what we end up with is R2 and R3 coming out at me, and then R4 and R1 going back, okay? And hopefully the Newman projection makes that a little easier to see. If I'm eliminating, you know, this is going down, this is going down, okay? And so there's no bond rotations that can occur because of this concerted single transition state. And so, so what happens? R3 and R4 come down a little bit. R1 and R2 go up a little bit. And what I end up with is something like this. And so this is an alkene Newman projection, which we haven't really drawn, but we can do it for sure. So there's R3 and R4 on the left on the front carbon. I got my back carbon, and R1 and R2 are in the same plane. We'll offset them a little bit so we can see them. So R1 and R2. And so the point is that they're on the same side of the alkene, okay? So when you're trying to think about the geometry for the E2 elimination, okay, do not, do not despair. So orient the substrate in the antiperiplanar conformation. So CH, CX, antiperiplanar, okay? And then ask yourself the question, which substituents are on the same side, okay? And so, you know, R3 and the line wedge diagram on the left here are coming out at us. They're on the same side. You can see that hopefully more clearly in the Newman projection, okay? R1, R4 on the same side. Again, hopefully obvious from the Newman projection. So, you know, the thing that you want to do, and this is actually one of the questions on the practice exam relates to this point exactly. So I'd encourage you, you know, to be able to work that. But, you know, if I had basically something like this, call this a methyl, and call this a hydrogen. Let's call this a methyl, and we'll call this just give it something different here. We'll call it ethyl. Not very creative on my part, but if I had that substrate, right, and we said, okay, what's the alkene geometry? The alkene geometry is going to matter, or there's going to be one that you need to worry about, right? And so how do you get there, right? How do you think about that? You need to get this, into an orientation where those two are antiperiplanar, assuming this is the one that will, let's assume that's the proton we'll remove. Okay, not always the case, but we'll say that's the one we're going to get. How do I figure out what the alkene looks like? First step is to draw it in this type of conformation, or from that type of perspective in that conformation, okay? And if you can do that, then hopefully you can get to the right geometry, right? And, well, I did not get, I have a 4-page review and we got through 1 page. So I don't know, I feel bad for the kids in previous years. All right, so maybe what we'll do is, let me look at my notes, but I think Wednesday is the material, if it's new, is definitely got to be, not going to be on the exam. I need to see how many things we have left here, but we may finish this on Wednesday. Yeah, we can afford to spend some time on this on Wednesday. So we'll finish this review on Wednesday. I'll stick around for office hours. I'm gonna hang up and come back around 10:25. And yeah, I'll see you guys then. Okay, bye.